All right, so thanks for sitting through that. Welcome back from spring break. This is always like the crunch time of the semester. So I hope that the rest of the class we'll be doing, difficult things because it's a difficult class and difficult subject, but fun things as well. That's the idea. Um, just to remind you what I said in my announcement yesterday, Zoom's designed mostly for me to be able to record this stuff because that's the easiest way that I figured out how. Um, and so it works in a pinch if you're sick and don't want to come to class, or you have an interview and you're traveling or something like that. But the thing that you miss when you come on Zoom is, like, I know for me as well, if I have a Zoom meeting and I don't have to have my camera on and someone's just talking at me with the screen share, it's hard to pay attention, right? And it's hard to actually sit and think through things. Whereas when you're in class, you've got this piece of paper in front of you and you're talking with your neighbors and trying to figure out problems. And so that's why I think that in person is far superior to just coming on Zoom. So again, like, I'm not going to restrict it at all, but this is just your friendly reminder that the way you can best succeed in this class is coming to class. Okay, so today we got to go over Kruskal's and Dijkstra's algorithms just because I kind of messed up. And I want to make sure that we really get it before you go off and do your video. Yeah, so we're going to briefly talk about how Kruskal's works. And I'm going to kind of hand wave you through union find, which is a data structure. And then I have an in-class activity that we're going to do for the rest of the time. Maybe. We'll see how fast that goes. Okay, so we're looking at minimum spanning tree, which is how can we find a spanning tree of a graph that covers every vertex, but doesn't have cycles. And when we're looking with weighted graphs, how can we choose those edges so that the weight of the tree, if we add it all up, that weight is minimal, so that we can't find something that has smaller weight. So for prims, the idea is we have to start somewhere. So we choose a vertex and we choose the smallest weight possible that we can find around it, then add that smallest vertex, as long as it doesn't introduce a cycle. That's the idea for prims. For Kruskal's, the same idea applies, right? Where we're looking, instead of starting somewhere and choosing one of the options available to us, we look for the smallest edge, grab that. And that continues. So that same idea is not wrong. It's just the details were a little bit lacking. And so the main steps are, first we sort the edges. So that way we can always choose the smallest, right? So we always want the smallest when we're looking at Kruskal's. And then this is the question that the video does not do extremely well on, which is we find that smallest available edge and we look at the vertices associated with it. And we ask, are these two already connected in our tree or not? If they are not connected in our tree, then we add it. We take that edge. If they are already connected in the tree, then we don't. That's the idea. And the way that we ask these questions, the question of, are these two vertices connected in our tree, we use union find. And so that's a data structure also known as disjoint sets, which checks, given two things, are they in the same subset? So are these two nodes already in my tree? That's what we're doing. Yeah, and so I have references here. It's a little bit tricky, but the idea is we could store it in like an array and then represent the tree like this. So like we have a tree of 3, 5, 6, 8, and 9. And we see that 3 can point to 5. So this number here indicates this is the root of our tree. The thing at index 5 is the root of our tree. The thing at index 8 points to 9, which points back to 5. So that's part of the tree. So we get something like 5 is the root, 3, 6, and then 9, and then 8 points to 9. So we can have a tree that way. And so it makes it easier to do this checking of are these two things in the same set? And so it's also called the disjoint sets data structure. Okay, so the union find, that's the nitty-gritty details of how do we answer this general question of how do we check if these two things are in the same subset. But the broader idea is we choose the cheapest edge and then ask that question of, are these two in the same tree already? So we use a data structure called union find or disjoint sets in order to accomplish that. Okay, so, and then Dijkstra's shortest path is all about, we start somewhere, we want to find the shortest path tree from one node to every other node in the graph. And the idea is there, we have some chart of distances, and then at every step, it's also a greedy algorithm where we choose the smallest possible distance, and then we update the table continually as we go until we find our shortest path tree. Okay, so I've got an activity to help us cement this now. I wanted to keep, we had like sorting spree, so I wanted to keep the alliteration. So we've got graph gauntlet. So we're going to do this once with Kruskals and once with Dijkstra's, where I've got some pseudocode here on Canvas. You can download it. And I'm going to, in a minute, I'm going to ask for you to congregate yourselves into groups. And then I'll tell you 1, 2, 3, and you get assigned that one. You're also free to look at the others to kind of compare and contrast. And so this is practice in like reading pseudocode. So I've given you pseudocode, and maybe choose one of the graphs from the packet or make up your own and run through the algorithm using this pseudocode. So we should have a broad understanding of how the algorithm works. Now it's your job to actually reference an example, which shouldn't be too different from what we've talked about, and make it happen. So we'll do that once with Kruskals and once with Dijkstra's. Okay, so get into groups, and then I will walk around and tell you 1, 2, or 3. All right, thank you for participating. Thank you for playing. So since now you all are experts in Kruskals, I'm not going to talk about like how, I'm not going to ask your groups to tell me how does the algorithm work. I'm going to ask you, what do you learn? Because it's difficult to stare at pseudocode and try and figure it out. Did you learn something about how union find works or disjoint sets? What stood out to you? That's what I'm looking for each group. So I think we have 1, 2, 3, 4, 5, 6, 7, 8-ish groups. So which group wants to go first? What'd you learn? Yeah.
You wanted to be to if we're not the most focused in the moment, to be extra careful to double check the cycles.
Double check for cycles. Okay. And did that play into the pseudocode that you were following?
Well, yeah, we're trying to follow the pseudocode. But yeah, we're just kind of going a little bit too fast.
Okay. Yeah. Always good advice. Yeah. Mm-hmm. Yeah. Yeah. Great. Who's next? Yeah. Yeah. Wait, let's see. Insert. Oh, no. Why am I doing this the hard way? Let me type. And then I know someone else said like the colon equals or the colon dash. That's something you learn as you read more pseudocode, where that's basically defining something. Which is it the same thing as just equals? Yeah, pretty much. But it's something that may be specific to pseudocode. Other insights, yeah.
Some common sense to us, such as determining whether like an edge is already in our subtree. It's much more complicated for the computer to do. With our pseudocode, those, I guess, initializing several arrays. So it was interesting to see how to translate what's common sense to us to something algorithmic for a computer.
Yeah, absolutely. Yeah, that's one of the things. So, like, as you're designing algorithms, you have to keep it in mind. Like, is this a simple task? Is it trivial? Or is it not? So to our brains, when we look at this graph, we could find the smallest, add it to the tree. But that breaking it down, more complex. That's why we have to talk about this. Yeah. 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 Yeah, so some of you got a more detailed pseudocode of like how union find or disjoint sets works. Some of you just got like the overview. So yeah, so make sure you go home later and look through the different pseudocodes to convince yourself, oh yeah, I was doing that. It just maybe is more high level or it's more low level now. Other insights? Okay, cool. Sounds good. All right. Now let's do it for Dijkstra's. So inexplicably, there's only one eraser in the classroom. So maybe feel free to trade it around. You can keep the same graph, but I now have two different pseudocodes for Dijkstra's, one which uses a priority queue, one which doesn't. So I'll go around and say 1, 2, 1, 2, and we do the same thing. All right, so we've got the three, let's see. So for no priority queue, we have just distances and the previous and something queue. For priority queue, we have distance previous and an actual priority queue. So someone tell me what's the point of the previous thing? What's the point of the distance thing? What's the point of having queue? Just like in plain words, yeah.
For here, for both the distance, you're keeping like a running total. The total weight, and you not going to get that much from whatever starting point you have. And then previous is the node that you went through before that.
So that's kind of like a map, how to get there. So someone with a priority queue, tell me what's the point of the priority queue? What do we use it for? Why bother? Okay. Mm-hmm. Yeah, so remember when we talked about it on an intuitive level, there's this idea of we've got unvisited vertices. And as we go through the graph, we want to make sure to visit every vertex. And so as we go, we need to choose which vertex to visit next. And what the priority queue is, since we've got that table of distances, I believe we enqueue it with the distance is the priority, right? And so if we find the next thing to visit with smallest distance, that's the greedy aspect of Dijkstra's algorithm. So let's see, how do I want to write that? Choose unvisited vertex with smallest distance. And that's the priority. So the reason for the priority queue is to choose the next unvisited vertex. That's why we've got it. And the priority being the next smallest distance. What about the version without a priority queue? Which groups did that one? Okay. I know there was another group that did it. The one without the priority queue. Okay. So yeah, I want to know do you do the same thing? Does it do the job in a similar way? How is it different from using this idea of the explicit idea of the priority queue? Yeah, sure.
Instead of just having minimum, kind of have to do more comparisons. I suppose would be less efficient than what we have at the moment, but
Mm-hmm. So it's kind of doing the same thing, just maybe a little bit extra work.
or maybe
Or-
the work is just like,
I mean, maybe
It's the
maybe we
same.
maybe we offload all that work just into priority queue and just wrap it around and say priority queue handles all of that.
Yeah.
Any other ideas? Any insights for how is running through this algorithm with explicit pseudocode? Was it what you expected? Do you learn anything new? What insights do you have?
Like this one translates code a lot easier.
Mm-hmm. How come?
I find it harder.
How is it more algorithmic?
Here, definite steps that requires
Mm-hmm.
addition and.
Yeah, yeah, and so this is something that you'll see in pseudocode, where sometimes it's very explicit, where it seems like you could translate this to like Python or C++ or something. But others are at a much higher level. So this is also one of the things to practice with this exercise of exposure with different kinds of pseudocode. Yeah, and where this has like the actual dictionaries and stuff. What other insights do we have? Yeah. Mhm. Shortest path didn't use the distance. This is the without.
Yeah.
So it returns all these distances. And then I think this is how you actually get the tree. Yeah. Yeah, so we've done all the work, we've constructed all our tables, and now we just need to read from them to get the tree. How do I want to write that? Any other insights? Okay, I'm happy with that. When you go home today, just look at the other pseudocode algorithms. You were assigned one of them. Look at the other options. What's other ways of looking at it? Especially if you had a priority queue, look at the way the other one works and vice versa, just to familiarize yourself with it. That may be something I ask on a test. Let's see. All right, so we're not going to get to the packet problems, but I do have very important reminders for you. One of which is that you have to meet with me to get approval for your project idea by this Friday. So I put a link to my calendar appointments in the Canvas announcement. So meet with your group. I prefer that your whole group is there. If maybe one person's not able to attend, that's okay. But I prefer that the whole group is there. That way, you all get a chance to contribute and talk about it. also the student research showcase thing that you get extra credit for, talk with me first. Yeah, I just want to talk with you before you submit that application. So yeah, that's due by Friday. If you don't have it, then that's not good. So make sure that you do it. Make an appointment. And be working on your graph video. That's due next Friday. So now we've all kind of got a good understanding of how these 3 algorithms work. So start working on it. Yeah, I'll leave the last few minutes. If you want to meet up with your group and schedule a time to meet and work on it, do that. Other than that, thank you, and I'll see you on Thursday.